Ladies and gentlemen, welcome back to Engineering Dynamics. In this video, we will be talking about continuous systems and how to get the eigenfrequencies and eigenvalues of those continuous systems. So in the videos before, we talked about how we can get the eigenfrequencies of systems that are discrete. So we had point masses and we had to know, we wanted to know how to get the eigenfrequencies and eigenvectors or eigenshapes, or better to say eigenmodes of those systems. But now we want to work with continuous systems. So a continuous system is basically an infinity of masses combined together. So we technically would find also an infinity of eigenfrequencies and eigenshapes. This cannot always be done analytically, so we will need some method to discretize our system again and get the eigenfrequencies and eigenvalues. But for some solutions, for example, like with the bar, we will get analytical solutions of those eigenfrequencies and eigenvectors. So let's start with a simple bar example of a continuous systems where we will find the eigenfrequencies and eigenmodes. So again, we said we're talking about continuous systems. Let me make it a bit bigger, about continuous systems, and especially we will talk about a beam. So in this case, we propose a fixed beam at the end and a free end on the other side. So it's clamped and free. That's why we call it clamped free. If we want to get the analytical solution, we first have to get the differential equations that governs this system. And we know some of those equations already, and we will now combine them to get the partial differential equations in space and time of this beam. So we know that the sigma, so the stresses, are the normal forces divided by the area. And the strain is just a space derivative of our displacement. Because displacement alone is not enough for us, we need a change of displacement. This is the strain. And the strain and the stresses are related by the Young's module. So sigma times E times our strain is sigma is equal to our Young's modules times our strain. And the normal forces, if we go from this to here, the normal forces are our area times our stresses, which again can be related to the Young's module and the strains. So if we have a system with an external load per unit length, so we have a force that goes on or is applied to our whole bar, for example, like wind or snow. This is our x dash, and we have a force at the end. For example, something is pulling. This is our n dash, and displacement is u dash. And mass dash is our density. So this is our density times our area. So it's the mass per unit length. With these equations, we now can construct a force equilibrium. So if we look at a very, very small part of our system, we know that we have a normal force in one direction and a normal force plus some, this is our dx, plus some length on the other side. We have an area here and we have an area there. Then we, of course, have our forces per unit length, and the whole thing is dense. And now we want to set this to our equality. So this will be our basically Newton for our system. We have force in the left direction, force in the right direction, then an additional force acting on our whole system is equal to our mass times acceleration over the length, over the x. So it is a small mass. And we would like to know, well, what is this part? And this part, we do a linearization, like a Taylor expansion, where we have n plus x plus the derivative of n, partial derivative with x, times the x, and higher order terms that we just ignore, because we just take the first one. Knowing that, and inserting, let me remove this one, inserting this equation, right here, we will see that the normal force and the normal force cancels out. So we have just x plus our derivative with x is equal to mu dot dot. And now we know that our normal force is actually EA times our strain. So this is our EA strain divided by x. And we know that, of course, our strain is again u du dx. So we're left with x plus dEA du dx divided by x is equal to mu dot dot. U dot dot, this one is the time derivative, so derivative in time, because if we get from positions to velocities to accelerations, we derive with time. And what we are left with, if we insert everything we know about the strains and stresses, we will get this differential equation. Here we just have our forces, our accelerations, and our derivative in space with x and x. And now we can propose boundary conditions. So at some point we have a given displacement, or at some point we have a given force. Normally we say it at the end. So if we have a system like that, we can say, well, we have 0 displacement here, and we have a force of, for example, 10 Newton on the free end. Now we want to talk about the modes, the eigenmodes and eigenfrequency of our system. Let's propose that our area is constant. So we can remove, so this one, the area that we had before, this one and this one are the same. So we have a constant area, and that means the Young's module is not dependent on x. The area is not dependent on x. We just have du dx, and we derive it twice. Then we have the mass is equal to m times u double dot, and we propose no external loads. And the external loads, let's go back up again, remove all this. The external loads were this x dash that we had. And we propose we don't have it, so we're only looking at a very, very simple system. And this is true for x in 0 and L. And now we propose a separation of variable. So we have our displacement function in time and in space, and we propose, well, we should have a function just for our space and a function just for our time. So if we replace that in here, we have u is equal to fq. If we derive it with space, we get u is equal to dx, df dx. If we derive it twice, it will look like this, times q, because the function q itself is not dependent on x, on which we're deriving. So we're getting this one. The same is true for a derivative with time. So if we derive with time, we're ignoring our space function and only looking at our time function. So we're left with this one. And this is essentially equal to this function. So we can set this equal, put the f to the left, the q to the right, and we will get this equation where dash dash is equal to let's make this better, where this dash is equal to d squared dx squared, and dot dot is a derivative in time, so d squared d time squared. So dot is our time derivative and dash is our space derivative. So the most important part to understand is that we got to this point because we did separation of variables. Now we can use those two functions to get the eigenmodes and eigenfrequencies. So let's first propose that this system is equal, or we know that it is equal in space and in time. So for every time step and for every direction, for every x in space, they must be equal because we got it from here. This is only dependent on time, and this is only dependent on x, so on space. And this is equal to a constant, but we don't know that constant yet. But we can propose a general solution where we have some time function q of t and some space function f of x, where we have f sine times omega t. So this is our dependence on t. And for the space function, we have a dependence on x with some prefactor lambda. A and b will follow from the boundary conditions. and from the starting conditions, and C and D from the boundary conditions. So where we have zero displacement or a given displacement, and where we have speed or no speed. So from that, we can derive this function twice, and we will get this equation. And we know that if we look at this part, we know that K is equal to minus omega squared. If we derive this function twice, we will get this equation. So we have minus lambda, because lambda comes from the sine and cosine, which is equal to Km divided by EA. So if we just look at these two parts. And from that, we know that our omega squared, so this part, oh, sorry for that. We know that our omega squared, which is equal to K, is equal to, we have the K right here, is equal to lambda squared EA divided by M. So what do we know from that? We know from that the more the lambda and the omega squared are proportionate. This means that the faster we vibrate, so this is omega squared, the more waviness we will have in our space function, because the lambda is determining the waviness in space. So the faster we vibrate, the more complex our shape is. So now, starting from the boundary condition, let's draw our system again. We have zero displacements at time 0, and thus at any time, we have zero displacements at x is equal to 0 for any time, and this means that our space function at x is equal to 0 must be 0. So this means d is equal to 0. Let's look at our system again. We will jump back and forth. So we have, this is our function. If we insert 0, we will get here a 1, but it must be 0, so d is gone. Then we know that our speed at times 0 is also 0. So this is our force. So the derivative of there we have it, the derivative of L is 0. This means that our derivative of x is equal to 0, because we have no force at the end of our system. Then we have this function, so a derivative of that is equal to 0. And we can just say, well, c is equal to 0, but this is a trivial solution where we would not vibrate at all. So we're not interested in c is equal to 0, but we're interested in what lambda do we need to have so that our system is 0. Because we're interested in the lambdas, because the lambdas and the eigenfrequencies are related. And we will see that for a system that is clamped free, we will get this type of lambda. And we can insert that lambda into our space function. So this was our lambda, and we will get the solutions of our system. So we can draw them, and it will look, let's go back. It will look something like, this was very ugly. It will look, the first one looks like this. The second one probably looks like that, and so forth. So we will have many, or that's wrong. The second looks like this, and then it looks like that. So we will slowly shift the sign, or more and more compress the sinus. The eigenfrequency, where we said it before, where was that? Is right there. So the eigenfrequency is lambda times the square root of EA divided by M. So this is our lambda square root E divided by M. And now we know the eigenfrequencies and eigenshapes of our system. It's important to understand that we have infinitely many eigenfrequencies and eigenshapes. So this is why our lambda is dependent on n. So if we say we want the first eigenfrequency, we will get one specific shape for that function. If we want to say get the second, we will get another, and the third, the fourth, the fifth, and so on. So for a continuous system, we analytically proved that we have infinitely many eigenfrequencies. I hope this video gave you a better understanding let's summarize all again. Let's get rid of that. So we had a continuous system where we had the simple equations of our dynamics. We proposed a force equilibrium for a system like this, did some Taylor expansion, and got the differential equation in space and in time. We proposed that we have no external loads and our force on our area of our beam is constant. So we got this equation. We did a separation of variables where we had a derivative in space and derivative in time. And from that, we went to our general solution, did some algebra where we said, well, if this is equal to that, then this must be equal to that. And we saw that we have a relation between our waviness in in time, this is our omega in time, and the waviness in space. From that, with the boundary conditions right there, or this is our general solution, with the boundary condition that we had no force at the end and we have zero displacement at the end, we have at zero, we got an infinite amount of eigenfrequencies or lambdas, waviness in space, that would satisfy these conditions. And we can insert them back into our general solution and get our eigenfrequencies and get our eigenshapes. I hope this video gave you a better understanding about how to work with continuous systems and that we have infinitely many eigenfrequencies and eigenshapes. If you have any questions, feel free to ask them in the comments down below. Thank you very much for your attention, and I'll see you next time.